Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about standard molar entropy. Okay, entropy is a measure of the amount of disorder that a substance has. So let's say that we're talking about a solid. Okay, most solids, the particles are all fixed in place. They are allowed to vibrate a little bit, but they're not allowed to move. So if you have a fixed location, you're able to move a slight amount but not a lot, then you're not going to have a whole lot of disorder or a whole lot of entropy. If you do talk about liquids, liquids are free to move. Now, they don't move a whole lot. They move relatively slowly, but they are moving. And because you're able to move, you would have a higher amount of disorder or a higher entropy. If you talk about gases, gases are moving much, much quicker. And for a gas, you would have very high entropy. Okay, so what we're talking about here is the amount of disorder, the amount of entropy that a substance has. And what's really unique about the standard molar entropy is that you can, under certain conditions, have zero. You can have zero disorder. Okay, so let's say we go back to the solid. If we're talking about a solid, solids already have pretty low amounts of entropy, pretty low amounts of disorder, because you're fixed in location, but you're vibrating. Now, if you have a crystal, okay, not just a solid, but a special solid, a crystal. In a crystal, every single particle is in perfect alignment with everybody else. Okay, everybody has their spot. And that means that order-wise, very, very organized, very little disorder. Now, if we take that substance and we cool it down, as it cools down, the vibrations slow down. And when you hit absolute zero, it stops. So at absolute zero, if you have a perfect crystal, every particle is in the right place. That's the crystal part. And if you're at absolute zero, nothing is moving. So if everybody's in a perfect alignment and nobody's moving, then you will have an entropy of zero. Okay, so that's what we're saying here. If you have a pure crystalline substance and you're at absolute zero, your entropy will be zero. Okay, there will be zero disorder. Now, the reason why that's kind of cool is because if you have something with zero, as you start to warm it up, you can measure the amount of disorder that you have. So what you're able to do is say, hey, let's warm it up 100 degrees and measure how much disorder that brings in. So you can actually measure the amount of entropy. Now, we would like to be able to compare results, right? So if I take my substance, it's at absolute zero, it's a perfect crystal, and I warm it up, and I say that I have this much disorder, well, I would like to be able to tell someone else how much disorder I have, how much entropy, and have them agree with me. So what we need is to have like a standard stopping point. How warm are you going to warm it? So what we've decided is that we're going to do it under standard conditions. So your standard state is a pressure of 1 atmosphere and a temperature of 25 degrees. So I'm going to take this perfect solid at 0 Kelvin and I'm going to warm it all the way up to 25 degrees at a pressure of 1 atmosphere. Okay? And if I do that, I can measure or calculate a thing called a standard molar entropy. Standard molar entropy, symbol would be an S with a degree sign. Now, in order to have a standard molar entropy, this is the amount of entropy that you're going to gain if you have 1 mole of a substance, okay, hence the molar entropy because it's 1 mole, and you are only going to warm it up until it's at 1 atmosphere and 25 degrees. Those are standard conditions, hence the word standard. So standard molar entropy. You've got 1 mole, you're going to warm it up to standard conditions, and then you're going to measure how much disorder or how much entropy that you have. Now, the little degree sign, that's our way of telling the world that you're under standard conditions, 1 atmosphere and 25 degrees. Okay? So that's our standard molar entropies, and it turns out that you can look these things up in a table. Right? I have a very small table here, but you can get much larger tables, so that way you can look up any compound you want and see what its standard molar entropy is. Say for carbon dioxide gas. at 25 degrees and 1 atmosphere of pressure, you have 213.8 units of standard molar entropy. Now, the units for this thing are a little unusual. It is joules per Kelvin dot moles. So there's joules in the numerator, kelvins and moles in the denominator. Now, at this point, I'd like to pause for a second, because what we're going to do with these is very similar to what we do with heats of formation and standard Gibbs free energies of formation. The way the calculation works is exactly the same. And I've got videos that cover both of those. Okay, so I have a video that talks about what happens if you have a standard Gibbs free energy of formation and what happens if you have a heat of formation or an entropy of formation. So the calculations will work exactly the same. So if you're doing these problems, chances are that you've also had to deal with delta G of formation and delta H of formation. And so I've got links to those other videos in the description of this video. So that way you can see all three simultaneously. Now, there are some notable differences between them. Okay, first off, you'll note that these are not formations. There's no little F's, right? When you talk about standard molar entropy, there is no little change here because these are absolute amounts. You start with nothing and then you end up with a bunch, right? It's like if you currently have $0 in your pocket and at the end of the day you have $20. You wouldn't say the change in my money is $20. You would just say my money is $20, right? If you start from 0 and you go up to 20, you would just say, hey, I've got $20. You wouldn't say my change is $20. Okay, when we talk about the delta G and the delta H, they're a little bit different because there really is no point where the standard Gibbs free energy of formation or the standard enthalpy or heat of formation is 0. So what we have to do is we kind of have to set a ground state. We have to say this is what we're going to call 0 and we're going to measure from that. And the way that we do it is through formation reactions. So let's say that we wanted to form, I don't know, let's say we wanted to form some HCl gas. So if I wanted to form some HCl gas, I'm going to be forming it from some H2 gas and some Cl2 gas. Okay, this is a formation reaction. You're not starting with a crystal at 0 degrees Kelvin. You're starting with elements and turning them into the compound you want. Now, they're still all per mole, right? These are all molar. This is for making 1 mole of carbon dioxide, 1 mole of carbon dioxide, 1 mole of Fe2O3. So for this one here, if you're going to do a formation, you are going to be making 1 mole of HCl. So that is the same. So if I wanted to balance this, if you've got 1H, in order to get 1H over here, you'd have to have a half. And you got 1 Cl. So to get 1 Cl over here, again, you'd have to have a half. So these here are absolute numbers because you're starting at 0 and you're adding disorder. These are more relative. We've decided that the amount of formation enthalpy or the amount of formation Gibbs free energy that goes with an element is 0. So we call this 0, we call this 0, and then we can calculate any change based on how much is associated with the product. Okay, so this one here is absolute. These here are about changes. These are not related to formation. These are related to formation. Okay, the other thing that you have to watch out for is pretty much what I mentioned here, right? When we're talking about delta G of formation and delta H of formation, what we're really saying is that your elements have been defined as having 0. What's the heat of formation for an H2? 0. What's the standard Gibbs free energy of formation for an H2? 0. But when you come over here to the S's, your elements, let's look at the O2 gas, those values are not 0. Because if you started with a perfect crystal of oxygen gas, at 0 Kelvin, it has 0 disorder. As you warm it up, it goes from a solid to a liquid and from a liquid to a gas, so it does gain a whole lot of disorder, right? Here we have decided that the elements will be zeros, right? That was a decision, so that way we could talk about how much it changed by. When you're talking about standard molar entropies, these here are actual values that we have measured from 0. Okay, so there's a little bit of a difference there. because when you talk about these problems, we often leave the elements out of our tables because they are zeros. So the assumption here is if you're missing something from your table, then it's most likely a zero. Okay, that doesn't work over here. There are no zeros in my standard molar entropy table, like none. Okay, so let's say we want to talk about some problems. So we'll keep our table. Let's put our table here. So the question is, use the table of standard molar entropies to determine the change in the entropy for each of the reactions. So there's a certain amount of disorder related to the reactants, there's a certain amount of disorder related to the products, and I'd like to know how much it changes by, right? So this has no delta because this is the absolute disorder for each chemical. But if you're talking a reaction, now you're actually having a change because you have a bunch of disorder associated with the reactants, you have a bunch of disorder associated with the products, and you'd like to know how much it changes by. Okay, so what we're going to do is we're just going to look them up. So how much entropy, how much disorder is associated with a sodium hydroxide solid? So if I look at a sodium hydroxide solid right here, the amount of entropy, the amount of disorder, is 64.4 joules per Kelvin moles. So this would be 64.4 joules per Kelvin moles. That's the amount of disorder associated with a sodium hydroxide solid. Okay, how much disorder goes with an HCl gas? Well, again, you come to your table, you look up HCl gas, it's right here. The amount of entropy or disorder associated with an HCl gas is 186.9. So 186.9 joules kelvins dot moles. Now, these are your reactants. This is the disorder or entropy associated with sodium hydroxide. This is the disorder associated with the HCl. If I want to know the total amount of disorder for my reactants, I just need to add them up. Okay, so if we pull out our calculator, I've got 64.4 plus 186.9. That gives me 251.3 joules kelvins moles. This is the total amount of disorder associated with my reactants. Well, now let's do the same thing with the product side. I would like to know how much disorder goes with my products. Well, I've got two, sodium chloride solid and H2O gas. So if I look at my table, NaCl solid would be right here. The amount of entropy associated with a sodium chloride solid is 72.1. So 72.1, and the units are joules kelvins dot moles. Excellent. Now, let's look up the amount of entropy or disorder associated with water gas. Now, you do have to be careful because these tables will attempt to fool you. They'll attempt to trick you. In this table, I have both water liquid and water gas, and I only need the water gas. The reason why I put the water liquid in there is to attempt to distract you, to maybe get you to choose the wrong number. If I had been feeling especially like wanting to fool you, I probably would have put in water solid, water liquid, and water gas. So that way it'd be a lot more room for you to make a mistake. Okay, so when you're doing these, you have to be very careful if it's a solid, a liquid, or a gas. So if I look at this one here, H2O gas, the value that goes with the gas is 188.8 joules kelvins moles. So joules per Kelvin dot moles. And again, I would like to know the total amount of entropy, the total amount of disorder that go with my products. So if we take out our calculator, 72.1 plus 188.8 gives me a value of 260.9 joules kelvins dot moles. All right, so I have the total amount of disorder that goes with my reactants. This is how much I started with. I have the total amount of disorder that goes with my products. This is how much I end with. And what I'm looking for is the change. I started with roughly 250 and I end with 260. Start at 250, end at 260. How much did it change by? It went up by 10, right? Roughly about 10. When I do this calculation, I'm going to say the delta S for the whole thing is products minus the reactants. Now, the reason why we do products minus reactants is because in the end, you actually do have the products. So if you actually do have the products, you have all of the entropy that goes with the products. So you have 260.9 joules kelvins dot moles. Now, what have you lost because of this chemical reaction? You've lost the reactants. And if you've lost the reactants, you've used them up, right? There's none left. Then you've also lost the disorder. So if you're losing the disorder, you have to subtract it off. So this will be a minus 251.3 joules kelvins dot moles. Right? You're gaining products because you're making them. So that's why you're adding it. But you're losing the reactants, that's why you subtract them off. And if we do our subtraction, I've got 260.9 minus 251.3 gives me a total of 9.6 joules kelvins dot moles, which is what we had said, right? You start off with 251, you end a little bit higher at 260. How much did you gain? You gained roughly 10. So my delta S would be 10 joules per Kelvin mole. Okay, now, if you have watched the videos that talk about the heats of formation or the enthalpies of formation, and you watch the video on the standard Gibbs free energy of formation, then you know that we usually just reduce this down to products minus reactants. And so this can be a delta S equals products minus reactants. It can be a delta H equals products minus reactants, or it could be a delta G equals products minus reactants. All three of them work in parallel. They're all basically the same calculation. It's a little bit different conceptually. Like when we think about what the numbers mean, a little bit different. But how we use them is exactly the same. All right, let's say we look at a second example. Now, when I picked my first example, I was very strategic. I made sure it was a 1 to 1 to 1 to 1. Now I want to talk about what happens if you have numbers out in front that are not all ones. What happens if you have 3s and 2s? So the idea is going to be pretty much the same. Okay, let's split off reactants versus products. I'm still going to want to know the total amount of disorder or entropy for the reactants. I'm still going to want to know the total amount of disorder or entropy for the products, and I am still going to do the subtraction. Okay, the difference is the disorders in this table right here, these numbers are for 1 mole. Remember, that's how we defined them. We said that they are standard molar enthalpies, which means that they're good for just 1 mole. So if you're going to make 3 of them, you're going to end up with 3 times as much disorder. Right? If you're going to have 2 of them, you're going to end up with twice as much disorder. So we are going to have to take account for these numbers because the disorder here, the entropy here, is for only 1. If you've got a number other than 1, then you're going to have to multiply. Okay? So let's talk about the Fe2O3. If I go looking for Fe2O3, Fe2O3 is right here. So the amount of entropy, the amount of disorder that goes with an Fe2O3 is 87.4 joules kelvins moles. Now, that's the number for 1 of them, but I don't have 1, I have 3. If you have 3 times as many, you're going to get 3 times the disorder. Think of it like babysitting. Okay? Imagine the last time you babysat 1 kid. Okay, so you had 1 little kid, you're watching them. You know what little kids are like. There's a certain amount of disorder that goes with them. Now imagine instead of babysitting 1, you babysit 3 little kids. You know that you're going to have 3 times the chaos, 3 times the disorder, right? So if I'm going to make 3 of these, I'm going to get 3 times the disorder. Now the thing that you have to remember with these equations is that the 3 in front really means that you have 3 moles of the Fe2O3. The 1 for the carbon monoxide really means that you have 1 mole of carbon monoxide. The 2 means you have 2 moles of Fe3O4. And the 1 in front of the carbon dioxide really means you got 1 mole. So when I say that I'm going to multiply this number by 3, I'm really multiplying it by 3 moles. And I like that because I now have a mole here that'll cancel with the mole in the denominator. So mole and mole will cancel and leave me with just joules per kelvins. All right, so that's my first reactant. Let's talk about the second one. How many of the second reactant do you have? I have 1 mole of them. How much disorder goes with the second reactant? Well, you pull it out in your table. The second reactant is a carbon monoxide. So you go through your table, you find your carbon monoxide has a value of 197.7 joules per Kelvin dot mole. And again, you have a mole and a mole in the denominator, so they cancel. Right? 3 of these means 3 times the disorder. 1 of those means 1 times the disorder. So if you do pull out your calculator, I have 3 times 87.4 plus 1 times 197.7. That gives me a total of 459.9 joules per Kelvin. Right? All the moles are gone, so the only unit I got left is joules over Kelvin, so joules over Kelvin. Now, let's repeat the same process for the products. Your first product, let's change color, is an Fe3O4. So if I come to my table and I look it up, Fe3O4 is right here. The amount of entropy is 146.4. Okay, so the amount of entropy is 146.4. The units are joules per Kelvin dot moles. Again, that is the amount of disorder, the amount of entropy that goes with one of these, 1 mole of the Fe3O4. But I don't have 1 mole of it, I've got 2 moles. So I'm going to have twice as much disorder, twice as much entropy. So I multiply it by 2. If you move on to your second product, there is 1 of them, so 1 mole. And what's the disorder that goes with a carbon dioxide? You come to your table, you find carbon dioxide right here, and you find that the standard molar entropy is 213.8. So 213.8 joules kelvins dot moles. Again, you've got moles versus moles in the denominator, so they'll cancel. You've got moles versus moles in the denominator, so they'll cancel. That means my final unit will just be joules per Kelvin. And if we pull out our calculator, I've got 2 times 146.4 plus 1 times 213.8 gives me a value of 506.6 joules per Kelvin. Okay, almost done. Last step, I'd like to know the change. So if you're starting at about 460 and you're ending up at about 506, you're talking an increase of what? About 46, right? So it is going to go up, so it's going to be a positive answer. And you are going from 460 to 506, so it's about a 46 change. Easiest way to do it is by subtraction. So delta S naught, the change in the entropy because of this reaction, under standard conditions, 25 degrees and 1 atmosphere, is going to be the value for the products, because we're making the products, minus the value for the reactants, because you're actually using them up and these are disappearing. So my delta S is going to be products, 506.6 joules per Kelvin, minus my reactants. So 459.9 joules per Kelvin. And if we haul out our trusty calculator a last time, that is 506.6 minus 459.9 gives me 46.7. Joules per Kelvin, so my answer is in joules per Kelvin. Now, for these two, it did happen that both of the answers were positive. Your answer does not have to be positive. If you started off with a really high amount of disorder and you ended up with a really low amount of disorder, then you will get a negative. It will drop. Okay? But the calculations here are very, very similar to the heats of formation calculations and the standard Gibbs free energy of formation calculations. Right? We don't refer to these as formations because this would be more of an absolute amount of disorder with each of the chemicals, but the calculations do happen in a very similar manner. So, as always, I'd like to thank you for joining me here at Chemistry with Dr. Clark.